Swayam Prabha. Digital India. Educated India.
Hello and welcome to this course on gas turbines and jet engines. Okay. So, today is our 7th lecture and this is the second lecture of week 2, and today we are going to solve some numerical problems. We have already studied what is a standard Brayton cycle, then couple of its variants. So, regenerative cycle and reheat cycle. Now, we want to see how to solve problems for this regenerative cycle and reheat cycle. We want to know the solution procedure. Okay. We have already solved one example for the standard Brayton cycle. We will take up that same example, but with modifications necessary for regeneration and for reheat, and we can then compare the values. The purpose of taking the same problem is to be able to compare the values and see how the efficiency and work output changes. Okay. So, the concepts which will be covered are the learning the solution procedure for numerical problems of regeneration cycles and reheat Brayton cycles. Okay. So, I am just showing the problem which we had done in one of the previous classes. If you go back to lecture 4, it was solved at the end of the lecture 4. For a standard Brayton cycle, we had certain conditions. Inlet temperature was 300 Kelvin, pressure was 1 atmosphere. Okay. So, we had taken a pressure ratio of 10. Okay. Remember that the pressure did not play any role, the actual pressure value in the calculation, but the pressure ratio was the important term. Then maximum temperature was taken as 1500, which led to a value of T equal to 5, and ideal gas air was considered, and we wanted to find what is the efficiency and W net. Okay. So, we will use the same conditions in our next problem also. That is why I am just we are revisiting this problem. And if you remember what were the values of T1, T2, T3, T4 obtained, T1 was already known 300 Kelvin, T2 we had obtained to be 579 Kelvin, T3 was already known as 1500 Kelvin, and T4 we had calculated to be 776 Kelvin. I am again revising this so that this gets reinforced in our memory. So, when later on we can compare directly with the regenerative and reheat cases. Okay. And we had a net work output of 446 kilojoule per kg and the efficiency was equal to 48.2%. Okay. Keep these values in mind, or you can come back to this slide or to this point of the video and check the values again. So, now we will take up a modified version of the same problem, but now including regeneration. Okay. So, we have a regeneration cycle. I am directly starting with the diagram of the cycle on a TS framework. So, on TS diagram. Okay. So, in the actual problem solving case, the problem will be there and we will start again with drawing this TS diagram itself. So, now let us say that this was the original TS diagram 1 to 2, 3 and 4. Now, we will consider a case with 100% regenerator effectiveness. Okay. Regenerator effectiveness is equal to 1, which is the ideal case. Then apart from this, what conditions were given? The inlet temperature is 300 Kelvin, inlet pressure is 1 atmospheric pressure, maximum temperature T3 was given, or again for this case also it should be taken as same 1500 Kelvin, and pressure ratio R is equal to 10, and we will use air as the ideal gas, okay, which is the standard practice. So, now from 1 to 2 we have the compression, then from 2 to 5 we have the heat addition in the regenerator. From 5 to 3 is the combustion process, then from 3 to 4 is the expansion in the turbine, and from 4 to 6 is the heat transfer from the combustion products in the regenerator. Okay, let us emphasize these regeneration processes. One process is going from 2 to 5, the corresponding heat removal is from 4 to 6, okay, and then we close the cycle by using a heat removal at constant pressure going from 6 to 1. Okay. So, we will use a separate color as compared to the previous problem. So, we want to find out again similar to the previous case, what is the efficiency and what is the net work output of this cycle. One of the questions we can directly answer, we know that net work output is not going to change, okay, because the turbine work output also does not change, compressor input also does not change. So, net work output will not change, because all the parameters are similar to our standard Brayton cycle. What about the efficiency, that we will try to obtain. Okay. So, what were the parameter values taken previously? Same parameter values we should take for all this air standard cycle problem. Cp is taken as 1.005 kilojoule per kg Kelvin. Okay. Then gamma is 1.4. If R is needed, in this case not needed, R should be taken as 0.287 kilojoule per kg Kelvin, which is standard value for air, okay, capital R. So, R is the specific gas constant. Okay. So, with this we start again. Let me remind like what are the steps. We go step by step through each of the process, find out the important parameter at each stage. So, T1, T2, T5, T3, T4 and T6. Okay. If it is a new problem, already some of the values were calculated in the previous problem, but we will again quickly go through this, because this is the towards the beginning of the course. So, we should get familiar with how to solve problems like this. So, T2 by T1 is R to the power gamma minus 1 by gamma. Okay. R is 10, gamma is 1.4. So, this we can directly obtain, this is equal to 1.9307. Previously also we had obtained this same value, which gives us a value of T2 equal to 579.21 Kelvin. This is obtained using this value of the ratio and T1 equal to 300 Kelvin. Similarly, T4 by T3 we had seen, and again in this case also you can see that this is 1 by R to the power gamma minus 1 by gamma. Okay. So, which is 1 by 1.9307. Go to the next slide. So, since T3 is equal to 1500 Kelvin, given, it means that T4 can be calculated, and it is of course going to be same as the standard Brayton cycle value, okay, because nothing has changed up to this point. Now, we also need to know what are the values of T5 and T6, because those will be required, but for a ideal regenerator, okay, epsilon or regenerator effectiveness equal to 1, T5 should be equal to T4 and T6 is equal to T2, that we have previously learned in the previous class. Okay. So, we know that T5 is equal to what value? T4, which we have just now obtained to be 776.92, and T6 is equal to which value? T2, right, which we had obtained in the previous slide as 579.21 Kelvin. Okay. Again, I will remind all of you that do all the calculations in Kelvin, particularly when you are doing this ideal gas calculations, otherwise you will get incorrect solution. Okay. So, all temperature values are now known, T5, T4, T6, T2, T1 and T3, all of these are known. So, we can find out the net work output, which will of course be same. Let us write for the sake of completeness what should be the case. So, CPT, remember what is this? T3 minus T4 minus Cp T2 minus T1, okay. Cp T3 minus T4 minus Cp T2 minus T1. Okay. We already know all the temperature values, we will replace and you will get a value of 446.08 kilojoule per kg. Okay. Now, what about the heat input? Heat input is going to change. Heat input should be equal to Cp T3 minus T5. So, now the heat input is from 5 to 3 instead of 2 to 3, okay, from here to here. So, Cp T3 minus T5. We know what is the value of T3, Cp is 1.005 kilojoule per kg. So, if you are solving in kilojoule per kg using Cp, then your solution of work transfer or heat transfer will come in terms of kilojoules, okay, or kilojoule per kg of the working fluid, which is air in this case. So, this is kilojoule per kg Kelvin. So, this W net and Q in will come in terms of kilojoule per kg. 1.005 1500 minus 776.92. Okay, this gives us a value of 726.69 kilojoule per kg. Okay. So, now thus the efficiency is equal to W net by Q in. Once you replace these values W net and Q in, you get that the efficiency is equal to 0.614, okay, 61.4%. Let us see how this compare with the, how these values compare with the simple Brayton cycle. Okay. Simple Brayton cycle, what was the net work output? 446.08. So, it should be same here. So, that is same for both cases. Okay. So, simple Brayton and this is for regeneration. So, for simple Brayton it is the same, W net is same 446, which we expect directly also we could have stated, but because this is the first problem we have gone through the calculations for this. What was the Q in heat input? It would be different. Okay. So, heat input was 925.39 kilojoule per kg. 925.39 kilojoule per kg. Okay. This is considerably larger than the value for the regeneration cycle. So, we can see that almost 200 kilojoule per kg of heat transfer or heat addition has been reduced from the combustion process because of the regeneration. So, regeneration has resulted in much lower heat addition from the combustion. So, which will mean that much lower amount of fuel required, which translates to higher efficiency. Okay. And the efficiency in that case was something around 48.2. So, 0.482, 48.2%. Now, it is significantly higher because of regeneration, it is 61.4%. So, like this you can get an idea about how the efficiency changes. We know that efficiency will change, net work output will not change, but now you get an idea about what are the values involved and how these values change, what sort of changes we obtain. Okay. So, you can pause here for a minute and think about all these values and comparison with the simple Brayton cycle and try to get a feel for the numbers involved. Okay. We will move forward to a second problem, okay, based on the same framework or same say problem setup, but now for a reheat cycle. Okay. So, now it will be for a reheat cycle, and now in this case we have a standard reheat cycle. Let us say that this is the TS diagram. Let us call this as problem 3. This will be then problem 2, and first problem that we have studied was problem 1. Okay. We can remove this slide and come back to reheat cycle. And if we draw the reheat cycle, remember how it looks. So, there are two stages of heating and two expansion processes. The two expansion processes were to increase the work output, and two stages of heating is needed to have those two expansion, although we would not have liked to have, because it increases the heat input or heat requirement also. 1 to 2, 2 to 3, 3 to 4. 1 to 2 is the compression in the compressor, 2 to 3 is the first heat addition, first combustion process, 3 to 4 is the first expansion in the turbine. This process is known as high pressure expansion, or and the turbine is known as high pressure turbine or HPT, okay, high pressure turbine. Just as a side note, you should note down high pressure turbine. Then from 4 to 5 is the reheating process, which occurs at the reheat pressure, and then from 5 to 6 is the expansion in the second turbine. This is known as low pressure turbine, okay, low pressure turbine, and this is a low pressure expansion process going from the reheat pressure to the ambient pressure. So, the conditions which are given for the problem are similar ambient condition, T1 equal to 300 Kelvin, atmospheric pressure, ambient pressure is equal to 1 atmospheric pressure at standard conditions. So, pressure we will not need, but if in case it is needed, you know what is the ambient pressure. Then R, overall pressure ratio is given as 10, like in the previous problem. And what else was known? The temperature T3 or the T max, let us write this as T max, okay, which is more accurate. So, T max is equal to 1500 Kelvin. It is also stated that the reheating occurs at optimum pressure. Okay. Reheating occurs at optimum pressure. If nothing is mentioned also in a problem, we will assume that reheating is occurs at optimum pressure, but if some conditions are already given, the reheat pressure is given, then we have to use that condition. Okay, then you cannot forcefully try to assume that optimum pressure is used. Okay. So, reheating occurs at optimum pressure. We want to first solve the problem with optimum pressure, because That way we will get the highest work output, and then we can compare that work output with the previous cases. Reheating occurs at optimum pressure. Anything else which was there? So, T3 R, T1, okay, everything is specified. Again we want to find out what is the net work output, which we know that in this case it should change, and net and the efficiency, okay, thermal efficiency of the cycle, this also will change. So, whenever we are calling efficiency, this of course means from thermodynamic point of view, this is the thermal efficiency of the cycle. All these cycles are heat engines, remember, or they represent heat engines, devices which convert thermal energy into. So, partially the thermal energy gets converted to work, and rest of the energy gets transferred to a lower temperature reservoir. Okay. Let us start this. Again the first part of the calculation remains same, we will quickly do it. So, T2 by T1, just for the sake of completeness you can again check the previous problem also, r to the power gamma minus 1 by gamma. So, I am writing everything down, because that way you will know actually if it was an independent problem, a separate problem with separate values, what are the steps that are involved. Okay. So, T2 by T1 is equal to r to the power gamma minus 1 by gamma, r is given as 10. So, 10 to the power 0.4 by 1.4, which means that T2 is equal to, so exactly it will be the same value 579. So, this value we had obtained previously also, let me write it down. Okay, this is 1 point. This is 1.9307, okay, and that gives us a value of T2 equal to 579.21 Kelvin. You can check with the previous cases also. Here also it was 579.21 Kelvin for the standard Brayton cycle. Okay. Then what about T4? T4 and T6 are now not equal to the previous value, because there was no intermediate pressure and reheating again. Okay. So, for that we need to find out what is R A and R B. So, R A equal to R B for the optimum case, optimum condition, and we know that we will keep this figure. Unfortunately, we will again have to draw it, but it gives us, makes us practice this drawing these figures, which is very important. You should be particularly practicing this, drawing these figures. 1 to 2, 2 to 3, 3 to 4, 4 to 5. I am not repeating the name of the processes. At this point, it should be remembered by all of you. Okay. So, for optimum condition, R A equal to R B, and because we know that R A into R B is equal to R, this is optimum. Equal to R, this means that for optimum condition R A equal to R B equal to root R. We had derived previously also, right, and which means that now T3 by T1, sorry, T3 by T4 is equal to P3 by P4 to the power gamma minus 1 by gamma. P3 by P4 is R A, okay, which means that this is equal to root R to the power gamma minus 1 by gamma. Root R we can calculate. So, root of 10, R is given as 10. So, this is equal to 3.162, 3.162. So, if somebody asks what is the reheat pressure in this problem, the reheat pressure directly now we can obtain based on the pressure ratio, because R A is equal to P 3 by P 4 and P 3 is equal to 10 atmospheric pressure. So, P 4 should be equal to 10 by root of 10. So, in this case P 4 is equal to 3.162 atmospheric pressure, which is the reheat pressure. Okay. So, combustion pressure. So, now you have 3 levels of pressure. In previous problems we had 2 levels of pressure. Okay. The combustion pressure after the compression process and the heat removal, the pressure during the heat removal process, which is after the expansion of the turbine. Now, we have 3 levels of pressure, one is for the initial combustion, then one is for the reheating and one is for the heat removal. Okay. So, these are in this case this is 10 atmospheric pressure, then you have 3.162 as calculated, 3.162 or root 10 atmospheric pressure, and this one is 1 atmospheric pressure. Okay, good. So, this comes out to be equal to 1.389, from where we get the value. So, remember T 3 is equal to T 3 is equal to 1500 Kelvin. Okay. Let us write down on the side. T 5 and T 3 both are equal to T max, which is 1500 Kelvin. So, from this we get a value of T 4 to be equal to 1079.53 Kelvin. Exactly same way we can find T 6, but we also remember that for this optimum condition T 6 should be equal to T 4. Previous class we had seen, otherwise you can calculate again. T 6 should be equal to T 4. Okay. Both these are at the same temperature, which is 1079.53 Kelvin. Okay. So, now what is the net work output? So, now we have 2 work outputs and 1 work input. So, C P T 3 minus T 4 plus C P T 5 minus T 6 minus C P T 2 minus T 1. So, you can see that T 3 is equal to T 5 and T 4 is equal to T 6. So, which means that work output from the high pressure turbine and work output from the low pressure turbine are both equal. Okay. Both of them generate equal amount of work, and compressor work remains similar as the previous case. So, now we know all the temperature values T 1, T 2, T 3, T 4, T 5, T 6. You can replace the values and you will get net work output, which is 845.15. This is turbine work output minus compressor work input was 280.61. So, I am not calculating, but you can calculate, it will be same here also 280.61 okay, kilojoule per kg, which is equal to 564.54 kilojoule per kg. How does it compare with the previous cases? Previous both cases work output was same. Net work output was 446.08 kilojoule per kg. Here 446.08 kilojoule per kg. Now, instead of that we have 564. This has considerably increased, more than 25% increased or 20-25% increase has occurred. Okay, 564.54 kilojoule per kg. but we will see that heat addition also increases, right. What is the net heat addition? Cp. So, now we have two levels of heat addition, T3 minus T2 plus Cp T5 minus T4, okay. T3 minus T2. So, going from here to here, okay. And then T5 minus T4 is the second heat addition going from here to here. So, from this point to this point and from this point to this point. So, this again you can replace the values and this comes out to be equal to, or let me write down the breakup also, because this is interesting, you should know. 925.39 plus 422.57 kilojoule per kg. This 925.39 should be same as the standard Brayton cycle heat addition, okay, because that part remains same, but now we have an additional heat addition of 422.57, which gives us a total value of 13. So, considerably high value of heat addition 96 kilojoule per kg, which means that the efficiency is going to be low, because from here we see that so much heat addition has occurred that the efficiency is going to be low. So, I will write in this slide itself instead of going to a new slide. What is the efficiency then? Net work output by heat addition for this case, which comes out to be 0.419. Okay. How does this compare with the previous cases? For the standard Brayton cycle, this was 0.482. For reheat, we have obtained 0.419, and for regeneration, we see that it was highest 0.614. So, for reheating, this has decreased and is the lowest among all three cases, but the work output is highest. So, for reheating, the work output is, instead of 446, now it is 564.54, 4.54 kilojoule per kg, considerably higher, although it has come at the cost of efficiency. Okay, like this, you should be able to solve more problems, which will be given in assignment. So, please start working on the assignment problems and try to solve those problems, and I will also share set of additional practice problems which you can try. Okay. So, with this we conclude today's lecture. So, we have learned in this lecture how to solve various Brayton cycle problems. In particular, we have solved regeneration and reheat cycle problems and compared the results for the same condition, and for realistic conditions we have compared the result with the standard Brayton cycle case, and we have seen how the characteristic values change, how the efficiency and work output change for each cycle. Okay. So, these are the references, and then we stop today's class at this point. Thank you.